Welcome again to Physics 371 Online. Today we're going to look at the beginning of electrostatic fields. And I'll work through the first two items on this outline, on Coulomb's law in the electric field, and then on continuous charge distributions. This corresponds to the first section in Chapter 2 of the textbook. We'll start with something that should be a familiar topic to most of you from previous courses. Imagine a collection of point charges, and we'll call these point charges source charges, and then a positive test charge, capital Q, in their vicinity. We can use Coulomb's law to write down the force that a single stationary source charge exerts on the test charge with the familiar form given here. F is 1 over 4 pi epsilon 0 times the product of the source charge and the test charge divided by the distance squared, and then the r hat unit vector indicates the direction of this force. It works this way so that if the source charge is negative, that would mean the force on the test charge would be towards the source charge, and that would be in the negative r hat direction. Otherwise, if the source charge is positive, then the test charge is repelled and experiences a force in the positive r hat direction. Epsilon 0 in this expression is the familiar permittivity of free space constant. Note, in this expression and all other similar expressions that we will encounter, the script r vector does not start at the origin, but rather runs from the source charge to the test charge, or the point in space that we're interested in. Now we can take this expression that gives the force produced by a single source charge, and we can use it to calculate the net force exerted by all the source charges on the test charge. We'll have a term in this sum for each of the source charges, Q1 divided by R1 squared, Q2 over R2 squared, and so on. And we can write this force in summation notation by pulling the capital Q outside the sum and writing it in this form here, assuming that we have n of the source charges. Now this expression can also be written using a slightly different notation in a way that defines something that we're going to call the electric field. So here we have the same force expression from the previous slide, and we notice that capital Q is a property only of the test charge. Everything else in the summation is a property of the collection of source charges. And so if we factor out the Q, we can define the rest of the terms in this expression as some kind of unique property of the source charges. And that is what we call the electric field vector. 1 over 4 pi epsilon 0 times the familiar summation. Remember that when we do this kind of a calculation, and you will have some problems on the homework to do, it's a vector sum. And in general, for some arbitrary collection of source charges, it can be quite difficult to evaluate unless those point charges have some kind of symmetry. So another question you might wonder is, well, why bother doing this? What good is knowing the electric field of a collection of charges? Well, the expression above reminds us that the electric field multiplied by a charge gives the force on that charge. Here we were using the test charge. So that means that if we can calculate or measure the electric field of a collection of charges throughout space, then if any other charge happens to come into that region of space, right away we can calculate the force that it feels. And using Newtonian mechanics, we can find the acceleration and the subsequent motion of that charge. So really it comes down to wanting to follow the trajectory of charges that experience forces from other charges. And the electric field is this intermediate quantity that allows charges to exert forces on one another, or at least that describes the way that they do it. But sometimes we don't have just point charges to consider. We might have a system where the charge is spread out, distributed continuously through a region of space. Imagine taking a plastic rod and rubbing it with rabbit's fur that transfers charge now onto the plastic rod. So here imagine that you have some arbitrarily shaped object, and we would like to know the electric field at point P. How can we do that? Well, first, since we have a continuous distribution and we already know how to deal mathematically with point charges, let's divide the charge distribution into infinitesimal elements, dq, here indicated by a little square. Next, we can use our knowledge of the definition of the electric field to write the differential electric field at point P due to the differential charge element dq. To do that, we'll need to introduce this script r vector, and then we'll simply write down from Coulomb's law the definition for the electric field given by a tiny element of charge dq. So you'll see that if we remove the d's, we just get the definition of the electric field for a single point charge. But here, this works for a tiny element of charge. Finally, the last step is to take the expression for this differential electric field and integrate over the entire charge distribution, which should give us the total electric field. And so right here we have an expression that looks quite similar to the one we had for point charges, except that the summation has been replaced by an integral, and rather than having a discrete charge q, we have the charge element dq. Otherwise, everything's the same. Remember again, this script r vector in this case runs from a charge element to the field point P where we are trying to calculate the electric field. Now, we will write this integrand differently depending on the dimensionality of the charge distribution. And in our three-dimensional universe, there are three different kinds of dimensionalities that we can have. Of course, there is a zero dimension, which is just the point charge, but we already know how to handle that. For a continuous distribution of charge in one dimension, or a line of charge, we would write down this charge element as lambda dl, where lambda stands for the charge per unit length along that line. Now, it might look like I'm telling you that lambda is a constant, but that's not the case. To keep it clear here, I just write it as lambda, but lambda can be a function that varies along the length of the line of charge. For a two-dimensional system, which would be a surface of charge, like you might get if you rubbed a balloon in your hair, you'd get charge spread out over that surface, dq is written as sigma dA, where dA is a differential amount of area of the surface, and sigma is the charge per unit area on that surface. Again, sigma is something that could vary throughout that surface. And finally, in three dimensions, we have a volume of charge. dq, then in three-dimensional cases, is written as rho d tau, where rho, as you can guess, is the charge per unit volume, and d tau is the differential volume element. So we'll take the expression that we had for the electric field of a continuous charge distribution and just substitute the appropriate expression for dq. For the one-dimensional case, we just get this expression here where dq has been replaced by lambda dl. For the surface, we have dq replaced by sigma dA, and for a volume of charge, we see the rho d tau term appearing in the integrand. So, these are the starting points for finding the electric field of continuous charge distributions in 1, 2, and 3 dimensions. Study the examples in the textbook as you read it. Note especially how we can apply symmetry to simplify the solutions to these problems. And I'll also do some examples in class.